Right. Okay. This is one of my favorite topics in astronomy, I guess. It's something which has always appealed to me. So it literally asks the biggest questions of all, I guess, the entire universe. Where did it come from? Why does it look the way it does today? What will happen to it in the future, long after we're gone. So I want to tell you the kind of the story of how we arrived at what we know about the universe today. Okay, so there's a little bit of backstory to it. So I will set the historical scene for you. I will tell you a little bit about how we measure distances in the universe. This is crucial to cosmology. We have to be able to measure the distances of these things like stars and galaxies in the sky. So I want to tell you how astronomers do that in a very simplified way. This will involve talking about something called a standard candle, okay? And once we've done that, once we've understood that, we can talk about galaxies and redshifts. Galaxies are the means by which we know the universe is expanding. So I want to explain a little bit about how we know that. The prevailing theory of the origin and evolution of the universe is now known as Big Bang theory. And I want to tell you about what it is and what evidence we've got for it. Primarily, it comes from the study of this relic radiation called the cosmic microwave background. And we've now measured it so precisely that I can give you within like 1 or 2% the size and age of the universe as we understand it. That's not to say we've solved everything about the universe. There are, in fact, many mysteries still remaining. So you might have heard of dark matter and dark energy. And for the last bit, we're going to let our imaginations run riot a little bit. I want to ask the question, do we live in a multiverse? Okay. Now, when I talk to you about cosmology and the universe, as we understand it, you might think the universe is just everything that exists. And therefore, if it's something else, it must be part of the universe. So what am I talking about when I talk about multiverse? Is that not just the universe, but maybe in a different definition? Yes and no is the answer, and we'll get to that. Okay, so we'll talk about the multiverse at the end. I couldn't start this meeting without referring to Douglas Adams, and do you know what? It's his birthday today. So there we go. So space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemist, but that's just peanuts to space. That's from the Hitchhiker's Guide to the Galaxy. And again, big just is, there isn't a word for the size of the universe, really. Now, our earliest theories of cosmology revolved on common sense notions that the stars appear to move and the Earth doesn't. So the first kind of cosmologies of the universe, certainly in Western civilizations, was that we have a geocentric universe. Not everybody thought that. There are Greek philosophers 2,000 years ago who certainly believed that the Earth revolved around the sun, but the majority view, particularly because of a mathematician philosopher called Plato, was that, and Aristotle, was that the Earth was at the center. So in this picture, you've got the Earth, and the Earth is broken down into regions which consist of earth, water, air, and fire, okay? And it's all about like how everything wants to find its natural resting place. Heavy things fall because they're trying to make their way to the center of the Earth. And you've got the planets and the moon orbiting the Earth in spheres, okay, the celestial spheres, and they're revolving around the Earth. And you've got the stars in the outermost sphere, okay? And that was the prevailing view until the 17th century, until the evidence started coming in that this couldn't possibly be the system that we live under. This was supplanted by heliocentric theory of the universe. So instead of the Earth in the middle, you've got the sun. So the Earth goes around the sun, the planets go around the sun. The reason things changed was because of Galileo making observations of things like the phases of Venus. So with the first astronomical telescope, you've got Galileo observing that the planet Venus can undergo phases. Sometimes it looks like a little half Venus. Sometimes it's a crescent. Sometimes it's almost full. In the system where you've got the Earth in the middle, it doesn't work. If you've got that system, Venus is always going to show some kind of a crescent phase. It will never be behind the sun in that setup. So it's evidence that kind of changes the astronomers' thinking about the universe. So at least we've got a universe now where the sun is the center and the Earth is going around the sun. But that final sphere, the one which contains all of the stars, that, I guess that was what the universe is. Now, one of the other issues with switching from Earth-centered to sun-centered is that if the Earth goes around the sun, that means the Earth moves, and presumably the Earth moves a fantastic distance every year. So we now know that distance across its orbit is about 186 million miles. So if the Earth moves 186 million miles in 6 months, how come the stars don't move? How come they stay in the same place? There's this effect called parallax, where if you move the position of an object, you see a shift and nearby objects move more. So it's the same kind of effect. If you hold your thumb at arm's length and you blink, your thumb shifts against the background. And if you move it closer to you, it jumps further. Parallax is just measuring an angle. But for even the nearest stars in the Milky Way, that angle is minuscule. I mean, it is so tiny, it could not even be measured until the 19th century. So before we get into kind of like other aspects of this, let's talk a little bit about the angles involved here, okay? Now, astronomers talk about measuring angles in kind of degrees or radians. Let's stick to degrees because they're easier to understand, right? So you've got 360 degrees in a circle, okay? So if you think of like one of those degrees, that's a tiny angle. In the sky, 1 degree of angle, okay? So like the distance from your eye to the top to here, so that angle is 1 degree, okay? That would cover 2 full moons in the sky, if you can picture what 2 full moons would look like. The moon is about ½ a degree. You can partition a degree into what we call arc minutes, and you can partition 1 arc minute into arc seconds, okay? So there are 3,600 arc seconds in 2 full moons, right? So an arc second is tiny. So the Earth goes around the sun, and over a period of 6 months, the nearest star shifts in its position by just under 1 arc second. Now, because this is all trigonometry, it's all angles and distances, if that star moves by just under 1 arc second, you can actually calculate how far it must be away from the sun using trigonometry, okay? When this was done for the first star to be measured turned out to be 11 light years away. A light year is a phenomenal number of miles in kilometers. It is the distance that light traveling at 186,000 miles per second would cover in 1 year. Okay, so 4 years to the nearest star at that speed. I did work out how big and like that shift would be in terms of something like a pound coin. So if you want to think of a pound coin viewed from a distance of 4 miles, that's how big the shift is in the nearest star as the Earth goes around the sun every year. So it's an amazingly small angle, and no wonder it wasn't measured until the 19th century. Now, once you start measuring distances like that using trigonometry, that's the only direct way you can measure distances in the universe. We're actually using the baseline of the Earth's orbit. But what you can do is you can figure out other relationships in astronomy. So, for example, there's a class of variable star called a Cepheid variable. And in the 1910s, I think it was, an astronomer called Henrietta Leavitt discovered a period luminosity rule for these stars. She figured out that if this kind of unstable star pulsated and changed in brightness and decreased and then repeated the cycle, the length of that period correlated with how powerful, how luminous the star itself was. So what it meant was later astronomers like Hubble were able to look at the Andromeda galaxy, and he measured something like this. So this is actually a picture of a Cepheid variable. I don't know if this is coming across well on Zoom, but can you see it pulsating in the picture? Yeah. So This is actually taken by the Hubble Space Telescope, but Hubble did this measurement on one of those variable stars. And because of Henrietta Swan's kind of measurement, Henrietta Swan-Leavitt's measurements, you could figure out that if it took a long time to pulsate, it meant it was a very luminous star. And by figuring out exactly how luminous it was and comparing it to how bright it actually was in the Andromeda Galaxy, you could turn that into a measurement of the distance. The picture on your screen on the right is meant to sort of indicate this idea. If you've got a candle and you kind of know how bright a candle is when you've seen one next to you, if you see a candle far away, it won't look as bright. And you can kind of look at the more distant candle and figure out how bright it would have to, how far away it would have to be at that brightness shining. And it's kind of like that. It's a slightly more sophisticated version with the Cepheid variable stars, and there's measurement errors and all the rest of it, but it's a pretty good relationship, and it actually allows you to see distances out to tens of millions of light years from the Milky Way. Now, to calibrate it, you need to be able to measure some of the more nearby ones using parallax. So you calibrate the Cepheid variables nearby, and then when you can't measure the parallax to the ones that are much further away, you kind of trust the fact that you've got the measurement of the nearby ones correct. And actually, over the past 100 years, every time somebody develops a slightly better version of this period luminosity relationship, our knowledge about the age of the universe and the size of the universe also changes slightly, because everything we understand about it is based on these steps, these standard candles. We have other standard candles as well. So there are things like planetary nebula, which have a similar kind of period, they have a similar kind of size luminosity relationship. And there are other kind of threads to this, or other steps on the cosmic distance ladder. And they all calibrate each other. They're all kind of checks and balances to make sure that they agree with each other. So these are the processes, the standard candles that we use to estimate distances to objects beyond the Milky Way and into the rest of the universe. Now, our view of the universe is really heavily influenced by what we call look-back time. And you'd probably be aware of the fact that there's no now in the universe. Now is, I mean, I don't want to sound like all like metaphysical here or whatever, but there's no now. Now doesn't exist. When you look at the moon, you see the moon as it was 1.25 seconds ago. Okay, it's like you've looked back in time by 1.2 seconds. When you see the sun, you've looked back in time 8.3 minutes. And our view of the universe is like that. The further out you look, okay, that you get pictures of these things, but they're not pictures of now, that they're pictures of the object in the past. It's more extreme when you look at the stars. So in Orion, for example, you've got Betelgeuse at roughly 640 light years away. So in fact, that's a picture of Betelgeuse from like the Middle Ages. There's Rigel from 800, 900 years ago. There's the Orion Nebula before Magna Carta. You know, it's kind of like you're looking out into the universe, but you're also looking back in time at the same time. Andromeda Galaxy, 2.3 million years ago. What does it look like now? Probably pretty similar. Probably hasn't moved that much. Galaxies, satellite galaxies, a little bit closer to it maybe. And it's more extreme the further out you look. The furthest thing I've seen with my telescope, with my own eyes, is this thing. This is a quasar called 3C273. 273rd object in the third Cambridge Atlas of radio sources in the 1960s, okay? And it's 2.4 billion years ago, okay? So that's the distance. So every time we look out into the universe, we're measuring things earlier in the universe's history. And this is how we see things. The further back, the further out we can look, the further back we are looking in the timeline of the universe. Probably one of the most spectacular pictures of recent years is this one. It's the Hubble Ultra Deep Field. And just about everything you can see in that picture is a galaxy. And just to really blow your mind over this, if you can picture a pin, okay, hold a pin at arm's length, the pin head at arm's length would cover as much as the sky as that picture is showing you. So this is a pretty empty part of the sky in terms of the Milky Way. There's not many stars in there. But if you imagine that pinhead's worth of galaxies extrapolated all around the entire sky, you get the idea of how many galaxies are out there. Okay, there are trillions of them that we can see. And because you're looking at a pinhead's worth of sky, it's like you're looking along a pencil line of sky. So you've got some nearby galaxies in here. You've got some very, very distant galaxies in here. And there's another nice effect with this picture. Don't some of the galaxies look very orange and red? And that's not a kind of artificial effect. What you're seeing in that picture is red-shifted galaxies. So the light from some of those galaxies has been traveling through the universe towards us for billions and billions of years. And during that billions of years travel time, the universe expanded and stretched the light rays out so that if they were initially blue, they became more red as the journey for the light progressed. And how red they became depended on how long the light was traveling. So you get this incredible effect of looking deep into the universe and also back in time. The furthest galaxies in that picture are around about 13 billion light years away. Okay, or at least the light has been traveling towards us for 13 billion years. Okay, now at the start of the 20th century, we understood the universe to be essentially the Milky Way. What we think of the Milky Way now is what people used to believe the universe was. Things like what we now understand to be the Andromeda Galaxy. Back then, if you read kind of like old astronomy books, they were described as the Andromeda Nebula. People thought the Andromeda Galaxy was a nebula, a kind of cloud of gas within the Milky Way. The Milky Way was it. That was it. That was the universe. The sun was a star, definitely, and the Milky Way was made of millions of stars. But that was it. There wasn't like anything beyond that. That was the universe, okay? What really blew that apart was the measurements of the Cepheid variables to the Andromeda Galaxy. As soon as Hubble and others started to make those measurements, they realized that through the biggest telescopes in the world, the Andromeda Nebula was actually made of some stars. You could actually resolve them. And furthermore, you could actually begin to see that some of those stars pulsated. They were Cepheid variables. And the periods of pulsations suggested that the Andromeda Galaxy must be at least 1 million light years away, which is much bigger than we believed the Milky Way was. So almost 100 years ago, we came to the realization that the universe was actually built from galaxies, okay? And the Milky Way was one of those galaxies, but there were others scattered across the universe. So 100 years ago, all of these nebulas that we see across the sky, we suddenly found that they were actually islands of stars, some bigger, some smaller than our Milky Way. So the size of the universe, from our perspective, dramatically increased about 100 years ago. So I've mentioned redshift already, but just to kind of give you the big picture of how that might work, what kind of measurements astronomers do. When you measure, you can do things like flame tests in a laboratory on Earth. So I know, for example, sodium, salt, which is in salt. I was sprinkling some salt on my scrambled egg over the hob, and it burns with an orange flame. Okay. Now, if you've got sodium in the atmosphere of a star, okay, it doesn't burn with an orange flame. What it does is it absorbs orange light coming from behind it, from the interior of a star. So in the spectrum of a star, you'd see in the orange part of the spectrum some dark lines where sodium atoms have temporarily absorbed photons of light from the core. If you measure the same effect for a galaxy, you get a blending of all the starlight. So you get things like sodium, hydrogen, helium, carbon, nitrogen, oxygen. And each of those elements has its own characteristic bite taken out of the spectrum. Now, if you do that on Earth, you find that these lines are in a particular place. They absorb a particular color. However, if your source of light is moving towards you, or you are moving towards it, then those lines will be blue shifted. It's a kind of Doppler shift where the lines all move towards one end of the spectrum. And if it's moving away from you, or you are moving away from it, the lines are redshifted, okay? And there's a nice mathematical relationship between the amount of shift that you see compared to being on Earth, which translates into a velocity, a speed. So if you measure like a shift in the spectrum, you can change that into a speed, how fast we must be separating to produce that movement, okay? So red shift and blue shift. About 100 years ago, astronomers started doing this for galaxies, and you can imagine their surprise, because you maybe would think that some galaxies are moving towards us, some are moving away, so maybe some are red shifted, some are blue shifted. Well, apart from the Andromeda galaxy, just about every galaxy in the universe turned out to be red shifted. They were apparently moving away from us. This is a picture from one of the books that I had when I was growing up. And it's meant to demonstrate what a spectrum looks like. So in the picture on the right there, you can see the spectrum, and there's some dark lines in the spectrum, okay? And this is from a nearby elliptical galaxy, okay? Now, if you measure galaxies which are also elliptical but smaller, okay, maybe they're smaller because they're actually smaller, but on average, this type of galaxy is smaller because it's further away. So if you can measure the Cepheid variables in some of these, you can figure out the distance to them. And if you measure the red shift, you find that the shift is all being pushed that way in the spectrum. The lines are moving away. So look at the velocities. That nearby galaxy is moving away from us at 1,200 kilometers per second. The one at the bottom, 61,000 kilometers per second. If you plot the distance with the speed it's moving away, this is something that Edwin Hubble did when he was studying galaxies. So what he found was there was a trend. It turned out that if you could measure the distance and then plot the velocity, you essentially got a proportional relationship between the speed and the distance. Okay? Now you might think, well, what's all that kind of scatter? It's not perfect. And the scatter, we think, is mostly to do with the errors we make because we don't properly, we haven't properly calibrated Cepheid variable relationships. Okay, so we you know, there are errors in the observations we make that translates into the scatter that you see there. Okay, so how do you interpret that? If every galaxy appears to be rushing away from you, does that not make us like at the center of things again? And that's not the correct conclusion to take from this, because that shift in the spectrum could be caused by us moving away from the galaxy, okay? Not just the galaxy moving away from us. So it's a relative speed. Okay, now when Hubble did this and published his results, there's a Belgian priest called George Lemaitre who interpreted this observation as being the universe must be expanding. His idea was that this measurement that Hubble made is totally consistent with the idea that there is extra bits of universe being created in the already existing universe. So every galaxy would actually have the same view as us. If you were in the Andromeda galaxy, you'd measure a redshift for all the other galaxies around you as well. The reason Andromeda is different, Andromeda shows a blue shift because it's actually nearer to us and we're actually on a collision course with it. So we know we're going to merge with it, but as you get further and further away from our galaxy, it's the expansion of the universe itself which begins to dominate and over the individual motions of the galaxies. So where does the expansion happen? It happens everywhere. It is every point in the universe is expanding away from every other point. Even the space in your room is expanding. Now, I'm not talking about the oxygen atoms. I'm not talking about like your table, your chair or whatever. I'm talking about literally the fabric of reality, the underlying space-time of the universe in which everything is embedded. That's the thing that's expanding. So how come you don't notice it? Now, if you have a look at this graph here, you can kind of look at this, and as I do with my math students, I say, well, you can calculate the gradient of this line, the slope of this line, to figure out something about the expansion of the universe. And a modern day estimate for this would put it at 70 kilometers per second per megaparsec, right? That's a weird number, weird. I want to try and convey what that number means because it's quite an important number in cosmology. So this is how you can visualize the expansion of the universe, okay? Imagine a block of space about the size of the Andromeda Galaxy, if you can, okay? So a block of space, empty, about 3 million light years on a side, okay? So I'm literally talking about a cube, okay, like that. There we go. So it's about 3 million light years. A megaparsec is 3.26 million light years. So, okay, so think of it as being like 3 million light years on a side. Right, okay. So what happens? Every second, that block of space is getting bigger in each direction by 70 kilometers. Okay, what's that? About 40 miles, if you prefer. So every second, it's getting 40 miles bigger. Okay, that means over the course of your lifetime, okay, an empty bit of space in the room you are in will get bigger by 2 nanometers. Okay, now that's less than the size of an atom. Okay, so you're not going to notice space expanding in your room. Even of the age of the solar system, you're not going to notice the space in your room expanding. But when you look at a block of space that big, the expansion is 70 kilometers per second. Okay, and if you look at a bit of space 6 million light years across each side, it will be 140 kilometers per second per megaparsec. Okay, so it's only when you look at very, very big distances in the universe that you begin to notice that the space in between is actually doing something very strange. Now, one of the underlying principles of cosmology is this thing called the cosmological principle. So I'll just describe it very briefly. It basically says that every bit of the universe is the same as every other bit of the universe. Okay, that means if you look at this bit of the universe here and count the number of galaxies in it, for example, and you look in all directions in your sky, you'll see basically the same kind of density and distribution of galaxies as you would as if you'd picked that bit or that bit. Now, the reason astronomers make this assumption is because it makes the equations that Einstein came up with for gravity easier to deal with. If you don't have this assumption built into Einstein's equations, they become almost impossible to solve practically for the universe. Now, 100 years ago, when people started doing this, the cosmological principle was kind of like a guess. People hoped it was correct. But now that we've got these surveys of galaxies, and we now know about billions of them, it seems to be sound, actually. We were kind of like on the right track. So in 2021, we now think that the assumptions that Big Bang Theory started with are actually pretty sound. Okay, it's a firm foundation that the subject is on. So the universe looks the same. You could be 3 billion light years away from here and you look around the universe and it's still going to be filled with galaxies in every direction. You won't be anywhere in the universe and find an edge. And that's the other part of this. In the picture, it looks like if you were here, if you look that way, you're going to get an edge. That's not what we think the universe is like. There is no edge to the universe as far as we know. Okay, now that might turn out to be wrong. Okay, if the universe has a finite size, maybe it does have an edge, but we don't think so. The mathematics and the evidence don't support there being any edges to the universe. There's an observational edge. There's like a horizon that we can't see beyond, but there doesn't seem to be a physical edge to the universe that you could cross over and say, I'm outside the universe now. Okay, so we don't think the universe is like that. Now, Einstein came up with a theory of gravity just over 100 years ago, which basically said that massive objects distort the universe around them. And what we think of as being gravity pulling on things is actually objects trying their best to follow a straight line through the universe. So they can't, because masses distort their trajectory. So when you observe the moon, for example, it looks like the Earth is pulling on it mysteriously through some force, but actually the Earth is distorting the universe around it. The moon's just trying to move in a straight line, but that straight line is curved around the Earth because of this distortion. So Einstein's idea of gravity is like that. Mass distorts space and time dictate where the masses move. Now, when Einstein tried to apply this idea to the universe, he was a little bit shocked and dismayed to discover that his equations predicted that the universe should either be expanding or collapsing. And he didn't think it could be collapsing, because if it was going to collapse, it would have collapsed by now. So his equations were effectively telling him the universe should be expanding. But when Einstein came up with this idea of gravity, the universe wasn't known to be expanding. So he put this little fudge factor into his equations to keep it balanced, to make it look as if the universe was eternal and unchanging. And he called it the cosmological constant. So it was a bit of a cheat. He put it in. He didn't trust his own mathematics enough to be able to figure out that the universe was expanding. But other mathematicians did. Others took Einstein's equations and applied them and figured out, well, why don't you think the universe could be expanding? And they came up with versions of the universe where it was expanding, and they made predictions about it. And then when Edwin Hubble came along and discovered the expansion of the universe, these models suddenly became very popular. So George Lemaitre came up with this idea of an expanding universe. I'm going to try and demonstrate how it's possible for every other galaxy to be moving away from you and for everybody to have the same view. So here you've got some galaxies, some little circles, okay? And as time passes, all the galaxies just move further away from each other. So the amount of space increases. Now, if you're inside one of these galaxies, let's get this picture here where you can see the center circle. Suppose that's us. We're measuring redshifts in every direction, and the redshifts indicate that the further you are away from us, the greater the velocity of the galaxy. So the universe is expanding. But what if you were in a galaxy down here somewhere, down towards the lower left? What would they see? Exactly the same thing. So now we're in a galaxy that's moving away from them, okay? It doesn't matter where you are in relation to other galaxies, you're all going to get the same view. Every galaxy sees every other galaxy rushing away from them. That's a consequence of the fact that the space everywhere is expanding, okay? So that's what we mean by the expanding universe. Now, Big Bang Theory, when it came along, didn't prove popular with everybody. There was an English astronomer from Yorkshire called Fred Hoyle, and he put forward an alternative view. Now, Fred Hoyle, certainly earlier in his life, was an atheist. And he didn't like the idea that the universe had a beginning. Okay, so we'll get to that shortly, but I think part of his motivation for this was that he didn't like the idea of there being a creation. Okay, so he put forward an alternative view. He said basically it was ridiculous to assume that the universe was expanding, because in the past that meant it was created at a point. Everything that exists now emerged from a tiny point in the past. That was ridiculous in his point of view. He figured out that actually you could have the universe looking the way it does now by creating just spontaneously one or two atoms every so often within like a meter cubed of space. It doesn't have to be very much, but it's certainly more plausible than creating everything at once, okay? So this is called the steady state theory. And he actually was the guy who came up with the name Big Bang, okay? So he was very disparaging about it and referred to this expanding universe as the Big Bang theory. You know, what an insult. You know, everything is just appearing at once, the Big Bang. Now, Hoyle's theory said that this was an unreasonable process here, okay? So Big Bang theory basically says the universe was smaller in the past. That meant the density was very high. Things were closer together, hotter, more dense. Over time, the material that's there spreads out and thins out. So Big Bang theory makes very specific predictions about how the universe is going to look with time. It says it's going to be more diluted as time passes. Steady state theory says the universe, actually, you might have a region of the universe that gets bigger and bigger, but if you create new material within it, the density stays constant. One of the reasons why Hoyle preferred this theory over the Big Bang theory as well is that it's an extension of this cosmological principle. The cosmological principle says the universe looks the same in every direction at every point in the universe. Hoyle's idea was that the universe looks the same at every point in time as well. So you go back 100 billion years, 1 trillion years, the universe is going to look like it does now because new matter is being created, but the expansion carries it further apart, but new material is created over time, so it always looks the same. He saw it as a more perfect version of the cosmological principle. So he saw it as kind of more idealized in the Big Bang Theory as well. Okay, so these are the two competing theories, although the majority of astronomers tended to go with the Big Bang Theory. Now, Big Bang Theory makes very specific predictions about the makeup of the universe, the chemical makeup of the universe. I grabbed a copy of the paper which made predictions about the content of the universe in 1948. So I don't know if you recognize the names on the paper, but if you just read the surnames, it's Alpha, Beta, and Gamov. And there's a kind of joke in there, a very geeky joke, nevertheless. Those are the first 3 letters almost of the Greek alphabet. Now, I'll tell you the story behind that because it's kind of funny. Gamov was the instigator of the joke. Gamov was a noted cosmologist, but he was also a practical joker as well. So the 2 people who really worked on the paper were Ralph Alpha and George Gamov. But Gamov didn't want to miss the opportunity to play this joke. So he asked a colleague who had nothing to do with the subject at all, Hans Bethe, if he would mind putting his name to the paper so that he could do this joke. Apparently, Ralph Alpha was really put out, really upset with just inviting a random person into this very groundbreaking paper. Alpha was near the beginning of his career, and this kind of diluted his contribution he felt to the subject. So he told people about that years later after Gamov had passed away. Anyway, Bethe went on to he got interested in the subject after this and started to work on the subject. But anyway, there you go. Now, Big Bang Theory, because it predicts a hot, dense universe, you can actually figure out what happens if you assume you start the universe with just a soup of elementary particles at a very high temperature and density. What happens to those particles as it cools down? And it actually makes a prediction that 75% of them will combine to form hydrogen, 25% roughly will form helium, with traces amount of isotopes of hydrogen and tiny amounts of lithium. Now, bearing in mind that since the start of the universe, stars have been formed. Stars make heavier elements than hydrogen and helium. Apart from that, if you take into account the number of stars we see, this ratio of hydrogen to helium is absolutely on the mark. This is a really fantastic prediction by the mathematics of Big Bang Theory, and it's been observed. And the other amazing thing, I think, is that all of the material that we have in the universe was created within a few minutes of the Big Bang. So we've got elements, hydrogen and helium. All of that stuff was cooked up within 20 minutes. Anyway, there you go. Now, Alpha went on to another paper in 1948 where he made a prediction. He said that basically if you've got this hot soup of particles, this big fireball at the start of the universe, that fireball, as it gets diluted by the expansion, should still be visible as a form of radiation which permeates the entire universe. So he wrote a paper about it in 1948. It came just after this one, so you'd think people would be like really interested in looking for it, but it went largely unnoticed. So that relic radiation, it was eventually discovered in the 1960s by these 2 astronomers here, Arno Penzias and Robert Wilson, and they had pretty much discovered it accidentally. They were looking for signals from the Milky Way. They were studying the stars in the Milky Way, and kind of radio telescope behind them was used for that. What they found was this hiss coming from every part of the sky, and they had tried every means possible to eliminate what they thought might be like interference from local sources. I think they killed a lot of pigeons because there was pigeon poo in the telescope, and they thought the pigeon poo was emitting the radiation. Turned out not to be the pigeons. It was actually the relic radiation of the Big Bang. Now, this fireball that started the universe, by today, it's cooled to the point where it's only 3 Kelvin, 3 degrees above absolute zero. So the temperature of this fireball is now minus 270 degrees Celsius, okay? And it initially was probably gamma rays and X-rays, and as they get stretched by the universe, this radiation is now stretched into microwave radiation. So it's way beyond the visible spectrum, and you need special radio telescopes to be able to detect it. The particular pattern that it follows is known as a black body spectrum, and it just indicates that the universe was very, very hot and very thermally mixed, very uniform in intensity, a perfect blend at the start. Astronomers today study the cosmic microwave background, and because the early universe was so hot and dense, after the hydrogen and helium were created, they were essentially just the nuclei of those. That you have protons, which are the nuclei of hydrogen, and you've got two kind of protons and two neutrons stuck together, which make a nuclei of helium. Okay, and you've got electrons just everywhere. Electrons stop light passing through the universe. It's kind of like a fog. So you imagine trying to see in a fog. If you shine a light, your light just gets scattered. And that's kind of how the universe was for 300,000 years after the Big Bang. But then it cooled and the electrons joined up with the atoms, and then suddenly light can travel everywhere. It's like the fog suddenly cleared in the universe. Now, when we look back in time with our telescopes, and we use radio telescopes, we can see the microwave background at the point it cleared. So we can see back to 300,000 years after the Big Bang, and we studied the pattern within the microwaves. We can't see back further than that because it's kind of looking through a fog into the early universe. But the nice thing is the patterns in this early version of the universe were imprinted on it when the universe was microseconds old. So even though the universe was kind of like created everything in the earliest minutes, the pattern of whatever happened back then was imprinted on this background radiation, and we can study that and therefore figure out conditions earlier in the universe. This is a map of the cosmic microwave background. Now, when it was discovered, it was utterly smooth. We didn't have the precision to be able to measure differences, and that caused a problem for Big Bang theory, because what we need to happen is not to have a totally smooth background radiation. We need to see places that are a little bit hotter, a little bit colder than the average, because the colder regions are more dense, and we need slightly denser regions for things like gravity to pull in more material and to build galaxies eventually. If the universe was just completely smooth after 300,000 years, gravity wouldn't be able to make stars, gravity wouldn't form galaxies, there'd be no us here. So we need those density variations, and they were discovered in the 1990s, and we've since been able to refine them and measure them. And now a lot of our ideas about the early universe come from looking at patterns in the data from maps like this. So this is a map of the baby universe. Now, as Big Bang theory was being developed, astronomers were looking out into the universe and looking at galaxies, and there were a couple of kind of groundbreaking measurements that were made. The first in the 1930s was by Swiss astronomer called Fritz Zwicky, who studied galaxy clusters. Okay, so this is things like the Virgo galaxy cluster that you can begin to see at this time of the year. What he did was he measured the speed of galaxies within the cluster, how fast they were moving around each other. Okay, this is a local group of galaxies held together by gravity, so they're not expanding away from each other. Okay, so they're moving around each other, and what he figured out was they were moving too fast for, if the galaxies are the only thing in that picture, you could add up all the masses of the galaxies, you could estimate how much mass is in there, and that mass is not big enough to make the galaxies move as fast as they do around each other. So he inferred that there was actually as much as 90% of the material invisible in that picture. So if you can see all of those galaxies and 90% of something else is not visible, what is it? So this was called the missing mass problem initially. In the 1970s, the astronomer Vera Rubin started measuring the velocities of stars within the Milky Way. And stars in the Milky Way are kind of like versions of the solar system. They go around the center of the galaxy, and you'd expect stars near the center to orbit like Mercury, to go quite fast, and stars that are further away to be like Neptune, to move much slower because gravity is weaker further away from the center. What she found was gravity didn't behave like that, and that the stars further away, in some cases, were moving as fast or even faster than the stars closer to the center. So it's like the stars are disobeying the rules of gravity. We don't think that's happening. What we now think is that there is all of this material that we don't know about, that we can't see, in the Milky Way, distributed around it in a vast halo called a dark matter halo. Okay, so that additional material, the gravity from it, influences the orbits of stars within our galaxy. We've measured the same effect with other galaxies now, so we know it applies to other galaxies as well. There's a small group of astronomers who also suggest that this might not be because there is a mysterious form of matter here. Some astronomers suggest that we don't understand Newton's version of gravity well enough, or even Einstein's version, and that it's slightly wrong. When you look at big distances in the universe, that the rule changes for gravity slightly, and that accounts for it. But the jury is kind of still out on that. There's a tiny little bit of evidence that that might be the case, but the majority opinion at the moment, and the bulk of the evidence, suggests that dark matter is some weird new kind of particle which doesn't interact in any way except for its gravity. Okay, so it doesn't reflect light. We can't measure it in any other way. It just influences things by gravity. So dark indicates, well, we don't know what it is. We don't know what it is. And people have been looking for it for years at this point. Okay, how are we doing for time? Okay. So the shape of the universe. Now, shape to a mathematician doesn't quite mean maybe what the everyday usage of the word means. Okay. So I've got some cartoons on the screen there. So we think of things like a sheet of paper. If you kind of like bend it or fold it, you can imagine changing the shape of a piece of paper by doing that. 3D space. How do you visualize 3D space being curved or bent or distorted? It's harder to visualize, but the 2D analogy would be like you see in the picture. You can imagine in flat normal space where the rules of geometry and Euclid and everybody apply. Everything you learned at school, like the angles of a triangle, adding up to 180 degrees. Remember that one? Those are the rules of flat space. And that's the universe we think we live in. But if there was enough material in the universe, because mass actually distorts the shape of space, you might imagine if you've got enough mass, you would distort space enough so that the angles of a triangle don't add up to 180 degrees. Space becomes distorted to change the way the rules of geometry work. I mean, it works on a sphere. If you've got a sphere, okay, I'm going to try and draw one here. On the Earth, here we go. Here's the Earth. Here's the equator. Here's the North Pole. If you've got somebody standing here and somebody standing here, and you try to walk parallel to that person towards the North Pole, if you both walk north, you're parallel, but you converge. And that's because a sphere is curved, but we're still talking about a 2D surface. The universe might be like that. So how you could think of it is, if you shine two lights parallel into the universe and they're really powerful, they might converge, even though they're parallel. They might actually converge to a point, despite your best efforts to keep them parallel, okay? So if the universe has enough mass, it might make it positively curved. If it's not enough mass, it might be negatively curved. What it seems to be is that the universe is flat, okay? Which means that if you shine parallel light beams out into the universe, they'll stay parallel, okay? That's the universe in which we live. And that's actually a big problem for the Big Bang Theory, because if you have a universe which is even deviating very slightly at the start from being flat, and you roll time forward 13 billion years, it will not be flat 13 billion years later. It has to be so tightly controlled at the start to stay flat 13 billion years later. So how do you do that? Do you really want a universe where everything has to be fine-tuned just to be flat for us 13 billion years later? Or is there some other explanation where it was bound to be flat? So that was one of the problems with the Big Bang Theory. How could it be flat as we appear to see it? There's another problem with the Big Bang Theory. There are others as well, but I'm just going to go into this one. It's called the horizon problem. When you look at the map of the cosmic microwave background, this region here and this region here, if you follow the expansion backwards, you might think they were both together at the start of the universe at the same place. That's not quite true. The universe, if you wind it backwards in time, these 2 points were still far apart at the beginning of the universe. And yet we measure them to have the same temperature now. How could they have the same temperature if they've never been in contact with each other? It's kind of like, I'm trying to think of this in terms of like making cups of tea. It's like if you make 2 cups of tea, okay, and you take them to different rooms of the house, if the room temperatures are the same, they're going to cool down at the same rate. And they're cooling down at the same rate because they were made from the same kettle of hot water, okay? We think points A and B were never together. They were never in contact at the start of the universe. And that might be something you ask about, okay? Why not? Was not everything together at the start of the universe? No. So how do they stay the same temperature, okay? Well, in the 1970s, an improvement to Big Bang Theory was suggested called inflation. And what this posited was that the expansion we witness now, okay, was actually quite leisurely compared to the expansion that took place in the first fraction of a second of the Big Bang, okay? So I want to try and convey a little bit about what it is. So the universe began, okay? I don't know how. Okay, sorry, I can't give you an answer to that one. The universe began, and almost immediately it expanded. Not by a little bit that we see now, but by this. It began that many seconds after the Big Bang, okay? That's 35 zeros if you're counting, okay? So that many seconds. It lasted for this long, and then it shut down, okay? During that period, the universe expanded from being about the size of a coin to the size of a galaxy. That's much, 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 much faster than the speed of light. Okay, but no rules are being broken. It's space that is expanding, not material, not mass. After that, the universe pretty much expands as we see it now, 70 kilometers per second per megaparsec. But in that brief instant, the universe was just, that was the bang. That was the bang in the Big Bang, okay? That expansion would have flattened any curvature that you would have had at the start, even the tiniest trace of curvature, okay? So if you could see a universe that was slightly curved, that curvature was suddenly flattened like that, okay? Those points A and B, they might have been together at the start, actually, and then they were flung apart 10 million light years away very, very quickly. And the energy from that process, when it shut down, gave rise to all the material. All that energy that was released created the mass in the universe. So this is inflation. It's an add-on. It's a bolt-on to the original theory. And it was brought in to explain certain problems with the Big Bang Theory. Cosmic inflation is pretty much accepted as mainstream cosmology these days. Okay, it seems like a long time ago now, but in the late 90s, we were starting to measure very accurately distances to supernovas in distant galaxies. So these are another kind of standard candle. So if you can measure the distance to them, you can figure out how far away the host galaxy is. And because they're so bright, they're visible right across the universe. What astronomers began to find in the 1990s were that the further out in time you looked, the fainter these supernovae actually turned out to be. They were much fainter than their standard candle status suggested. And because you're looking out into the early universe when you look back that far, that suggested that the expansion of the universe itself had changed since the early days. So roughly 8 billion years after the Big Bang, the universe's expansions changed in character and it began to accelerate. And that's the phase of the universe we currently find ourselves living in. So remember, gravity acts to pull things together. This is different. The universe might have collapsed if not for this. After a while, the material in the universe got so diluted that the energy inherent in empty space began to exert a pressure that was higher than the value of gravity from the objects within it. So that's something that kicked in before the universe, before the Earth was created. I just want to kind of finish by highlighting how little we know about the subject. So if you came here looking for answers, I'm sorry about this, but I've got virtually none to give you. The energy content of the universe is mostly unknown. Everything you see in the night sky, all those stars, the galaxies, the planets, me, you, the table in front of you, all of that consists of 4% of the universe. The rest of it, 96%, we currently don't know what it is at all. We're not even close to discovering what it is. How long this is sustainable in cosmology, I don't know. Okay, but you know, it's going to persist for a while. I really hope to find out what this stuff is before I die, but you know, I don't know. This is what we know about the universe. It's very precise. 13.79 billion years. That's the age of the universe. Plus or minus 20 million sounds like a lot, but it's just a fraction of a percent of the age of the universe. So we know the age to within very small margin of error. The size of the universe might scratch your head a little bit. The estimated diameter of the bit of universe we can see is 92 billion light years, but that's the observable universe. Now, how that works is this. We can see out into the universe, but we can't see beyond a certain point, because if something has taken, I'm going to say this correctly, if something is 13.79 billion light years away, okay, when the universe was, well, like now, its light will have taken the entire age of the universe to get here. So you can imagine here we are, and we're surrounded by something which is like a horizon. Okay, so if you're on a boat at sea, you've got a sea horizon. If you look around the universe, we've got a horizon defined by the age of the universe. So you might see a galaxy close to what appears to be the observable horizon. Okay, but just like a ship on your horizon at sea, you don't assume that the universe ends at the horizon. Okay, so what if you were an observer in a galaxy here? Well, you'd see us on your horizon, but presumably in the other direction, you'd see galaxies that way. So the distance from here to here could be the size of the observable universe, but likely it's much bigger as well. Now, if this distance here, if it's taken light nearly 14 billion years to cross that distance, during that intervening time, the object itself has gotten further away from us because the universe has expanded over 14 billion years. So those objects we see in the sky that appear to be 13.7 billion light years away are in fact now, because of the expansion of the universe, 46 billion light years away, according to the model. Okay, so the observable universe is one measure of how big the universe is, but it's not likely to be the full extent of it. And in fact, the universe may well be infinite in size. We genuinely don't know the answer to this at the moment. It might be just very, very, very big, but it might also be infinite. So what I want to mention is that one of the ongoing features in cosmology is something called the Hubble tension. So this number that I mentioned earlier as being about 70 kilometers per second per megaparsec. Actually, astronomers who study the microwave background and astronomers who study the standard candles of the universe, they're actually studying the universe for the standard candles, kind of like the modern universe, and the people studying the 300,000-year-old universe arrive at different values for this expansion rate. And this is called the Hubble tension, because it's measuring the Hubble constant. And it's now actually a significant difference between the two values. So we can't, at the moment, explain this away as being kind of systematic error, or it might be new physics at play. It might be we don't understand the early universe as well as we thought. So something's going to give, okay, at some point, but this tension exists amongst cosmologists today. You might be aware of Sir Roger Penrose, British mathematician, cosmologist, did work on black holes with Stephen Hawking and won the Nobel Prize in Physics last year. He has an idea of the universe where the Big Bang was not the true beginning of the universe, and that we live in a cyclic universe. It's probably not a new idea. I imagine people in the past thousands of years ago have suggested that, you know, the universe is a wheel or whatever. You know, you get different versions of this, but to pin it down mathematically, Penrose has done a good job of explaining why we might not be in the first iteration of the universe. Now, the way our universe works is that the Big Bang created all the material, okay? And then galaxies and stars formed. And what stars do is they basically turn the mass into radiation. Stars shine. So it's a case of mass being converted into light. And eventually stars die, they blow up. Some of them become black holes. So in the future, a long time in the future, you'll just have lots and lots of black holes around the universe. But Hawking showed that black holes actually evaporate, they emit radiation, and gradually, and then faster and faster, diminish to a point where they explode, and that black hole scatters its radiation across the universe. So basically, all the matter in the universe at some point is going to get converted into radiation. But at the same time this is going on, the universe is expanding and expanding and expanding, and the acceleration is getting faster and faster. So you're going to get to a point one day where every photon of light is expanded away from every other photon of light, and it in effect becomes a photon, just a single photon of light within its own observable universe. And under those situations, the universe has reached a point where it's maximum entropy, and the conditions in a universe like that are actually very similar to what we believe conditions were like in the Big Bang before. So if you've got a very, very old universe and time no longer has a meaning in that universe, then those are the conditions under which a Big Bang might happen. And under those conditions, a Big Bang occurs as the old universe dies. So this repeats, and there's no reason to think our universe is the same as the first one. So that would appeal to people like Fred Hoyle, I think, who wanted to have this idea of no beginning to the universe. So you've got this endless cycle of universes. Got to say, there's not a lot of evidence for this. Penrose and his collaborators, I think, are looking for patterns of earlier universes in the imprint of the cosmic microwave background, but at the moment there's nothing really conclusive. So why not just stop there? Okay, why not just have, you know, that surely is it. Why do we need to have like the idea of more universes? Now, I'm not going to like talk forever about this, you'll be relieved to hear, but I do want to give you a flavour of some ideas which might suggest that what we've described as being the universe might not be the only universe, okay? The multiverse is the idea that you might have what regions that we can see like the observable universe, but others, okay? And there's different versions of this, so I want to tell you about some of them. Okay, there's a really good book, in case I forget to mention it, by the astronomer Brian Greene. Okay, so have a look for it. It's been out for a while. You can probably grab it in paperback, and it talks about lots of these different versions of the universe. So it's the hidden reality, it's called. Now, this version of the multiverse just requires you to accept that there are regions beyond the observable universe which haven't kind of expanded to become in contact with us. Okay, so that left panel is our observable universe, but you could just imagine that beyond the horizon that we can see, there are other regions like that. So Brian Greene refers to this as like a quilted universe, okay? Or you could think of it as being like a patchwork, where each of those circles in the picture is like a version of a universe which is isolated from other patches. Now you might think, well, this is just the universe. It's just that you've got regions within it that are not in contact. But given that everything I've told you so far about cosmology has been about explaining where our patch came from, you might as well think of those other patches as being other universes, okay? Now, when we talk about the expansion of the universe, maybe it applies to those other regions as well, and gradually they'll merge with each other and we'll become a bigger universe that way, okay? And you might think, well, what's going on here? Well, another patch there. It's just that there's infinite numbers of these patches, okay? But they're separate. But as time goes on, they'll gradually blend together. But there'll always be bigger regions which we haven't made contact with yet, okay? So that's the patchwork multiverse. Now, how does that work? Right, okay, this might do your head in, so concentrate on this. I'm just gonna have a sip of coffee before I try to explain this. I made a universe. Now, it's a very small universe. This is a 10 by 10 universe, okay? Now, you've got to imagine this is kind of like an analog of the real universe. What quantum mechanics, the big theory of the 20th century, has taught us about space and time is that you can't divide space into infinitely small regions. So I've tried to capture that idea here by showing you a 10 by 10 two-dimensional universe. So each position in that 10 by 10 universe has either got a particle in it or it hasn't, okay? It's got a 1 if it's got a particle, it's got a 0 if it's empty, okay? Our universe is the same. Each location in the universe will either have a particle or it won't, okay? Each particle will be moving with a certain speed in a certain direction. It will have a certain energy. Quantum mechanics says you can't have an infinite number of values for that energy. It's quantized, okay? So you have basically, it's kind of like the volume digital, like my radio has like volume 1, 2, 3, 4. You can't tune it to volume 1.5, for example. It's like that for energy. So you've got gamma rays, X-rays, and so on, but you've got very definite kind of frequencies that you're allowed to have with these things. That means for my 10 by 10 universe, you've got a certain number of particles, there's a certain number of allowed energies and speeds. That means there's a finite number of rearrangements for the material inside my 10 by 10 universe, okay? And when you work it out, and the branch of mathematics called combinatorics tells you about permutations and combinations. It's the same maths that tells you your odds of winning the lottery, okay? Choosing 6 numbers from 49. Well, this is just choosing a number of particles from a number of available locations. In my model, there are 3.6 million ways to rearrange the particles. And because in my universe, I'm only allowing 4 ways of distributing energies, it means there are 87 million possible ways you can have the universe. In other words, if this universe, if everything extended infinitely, every 87 million universes, you'll get a copy, an identical copy of the particles moving in a particular way. So I hope you believe that for my 10 by 10 universe. And I've got some different versions of it down here. I've set it up in Excel and I just press F9 in Excel and it generates a new universe. So if I did it 87 million times, I'd get a duplicate universe. And what that's the equivalent of would be our universe. Our universe is much bigger, but the number of locations is finite. Okay, so imagine like all the billions of light years available in our universe, okay? You might conceivably have a particle and then there will be a number so big I can't even write it down as like zeros, okay? But you could mathematically calculate that. And they couldn't be filled with particles because then it would all collapse to be a black hole. So you can't even have like, for example, in my universe, I made it so that only half of the spaces had particles because in my laws of physics for my universe, which I created, you'd get a black hole if you had too much material in it, and that would be like our universe too. So anyway, are you ready for the number here? The same rules apply. If you've got an infinite or just very, very big universe, the same rearrangement of atoms and particles will exist somewhere else in this finite, in this possibly infinite space. So you can calculate precisely what where another universe identical in appearance would be. So all the particles have arranged themselves so that you are actually sitting and you've had the same life, the same experiences everybody else has. It's an identical copy, same stars, same rearrangement of everything. It's a different patch of the universe, but it's identical. And how far away it is this many meters. And that's a number which I have to write in mathematical notation. It's a number so big that there aren't enough atoms in our observable universe that if you turned all those atoms into ink, you wouldn't be able to write that number out. But mathematically, it's that many meters away in any direction you'd care to walk. You will eventually stumble across a universe in which you exist, your doppelganger. There's also a universe where everything was the same, but you didn't come tonight. Maybe you wish you were in that universe. Anyway, there you go. So that's a version of the universe. Now, there's just, I'm really not going to go into detail about these, but quantum mechanics, which I've mentioned already, has the idea that the wave function collapses. Now, what that means is quantum mechanics assigns a probability to basically experimental results in the universe. There's a famous thought experiment called Schrodinger's cat, and Schrodinger came up with this thought experiment because he didn't believe that quantum mechanics was an accurate theory of reality. It's basically that the universe is governed by probabilities. Okay, so you could perhaps think of when you're at school, you have this idea that a hydrogen atom is a proton in the middle with an electron going around the outside, and it's like a little planet being around it. Well, quantum mechanics does away with that. What it says is you might have this thing called an atom, but really it's kind of like the electron. You can't know where it is. You can't figure out exactly where it is. There's just kind of like a region around here where it might be. It's a fuzzy region, and the equation tells you the probability that it'll be here, or the probability that it'll be here. Not that it'll definitely be there. And because the universe is fundamentally built on probabilities, it means that within quantum mechanics, when you take a measurement, the probability part of it disappears, and nobody really understands why it disappears. The equations of quantum mechanics don't tell you why this should happen. And so you have various physicists who interpret the theory in a slightly different way. And one of the interpretations is called the many worlds interpretation. So what the many worlds interpretation of quantum mechanics says is when you make a measurement, okay, your measurement actually splits the universe into two pieces. And in one of the universes, the measurement you made corresponds to this probability, and in the other universe, it corresponds to this probability. You don't perceive the universe splitting off and branching, but that's what it's doing. Schrodinger's cat experiment basically sets up this fake experience where the cat is in a box with a radioactive substance, and the observer traps the cat in the box so that the radioactive decay, which happens randomly, either releases a poison or it doesn't after a period of time. So according to quantum mechanics, the cat is both alive and dead according to the equations. But obviously, if you open the box, the cat will be one or the other. Can't be both. So according to the many worlds interpretation, when you open the box and take the measurement of the cat, there's a universe where it splits and the cat is alive with you. And there's another universe where the cat is dead with you. And you don't perceive that. But this is happening. This branching is happening all the time. There's a movie which you might have seen called Sliding Doors. I think it's got Gwyneth Paltrow in it. And that's one version of how this reality might work. Back to the Future is another. Okay, so you get universes branching and splitting, and it's a staple of science fiction, this kind of many worlds. So these are genuinely different universes being created, and there's kind of like reasons why it might actually be true, but at the moment we can't test it. That might change in the future though. Inflation is something that I've mentioned. So this thing at the start, which basically was the bang in the Big Bang, inflated the universe to a huge size and then shut down, okay? Well, from our perspective, it shut down, but actually there are regions far beyond our horizon where inflation is still happening. And when it shuts down, it creates an observable universe. So it's always going on somewhere, and every time it shuts down, it's kind of like a fractal. It generates a universe. And each universe is distinct and separate from every other piece. And more interestingly, because of when it shuts down is kind of random, the way in which inflation shuts down defines the laws which operate in that universe. So you could have different pocket universes with different laws of physics, imagine that, different forces of nature at work in these universes. So there are lots of versions of it. They're all encompassed by this last one. The universe seems to be built on numbers. Mathematics, my subject, seems to be a very good way to study the universe. And that's actually one of the underlying mysteries that nobody's been able to figure out. Why do rules about numbers, like Matteo at the minute, he's learning about like, he's learning to count, he's learning about shapes, and it's brilliant to see maths being kind of like experienced by somebody for the first time. Why do numbers capture so much about the universe? One of the really controversial ideas is that the universe, the multiverse, is mathematical. Every possible mathematical combination of laws, of relationships between objects defines a universe. We live in a universe because mathematics is the foundation of the universe. And you could have universes which are based on different versions of mathematics. And collectively, that great ensemble of mathematical laws defines the multiverse. And we find ourselves in one of those pockets where we have this particular version of mathematics, but there are others. Again, there's a really good book by this mathematician, cosmologist called Max Tegmark, who is he's an absolutely serious cosmologist. But on his website, he admits that for every 10 serious mathematical papers he writes, he allows himself the indulgence of something like this, where he lets his imagination run and he comes up with ideas which might define the universe, but he's got no way of proving. And the only reason people take them seriously is because he is an absolutely serious cosmologist who generates great ideas about cosmology. So we might be living in a multiverse, and it might be this one, it might be one of the others, and maybe we'll know one day. But there we go, the end. I'm going to stop there.